Welcome to session 15 of Dr. Donald J. Wheeler's Understanding SPC seminar. This session continues the discussion of basic EMP studies by addressing how to create and use main effect charts and mean range charts. Next, several case histories will be reviewed to illustrate how EMP studies have been used in practice. Finally, Dr. Wheeler will skip to Chapter 16 to discuss the problems associated with the use of the Auto Industry Action Group Gauge and R&R study. This session will use Evaluating the Measurement Process, where we begin on page 73.
So what about main effect charts? Our next example will illustrate the use of the main effect chart, ANOME, to detect operator bias. 3 operators measured each of 5 parts twice. Right off the bat, we see reasonable parallelism, similar test-retest error. We can estimate sigma PE, R bar over D2 square roots of n sub r, 4.267 over 1.128 times 1, 3.8 mils. So our probable error is about 2.5 mils. We now know how close these measurements are. They're recorded to the nearest thousandth of an inch, and they're good to plus or minus 2.5 thousandths. However, the 3 operator averages appear to be slightly dissimilar. Operator A seems to obtain systematically higher values. So we might want to test that. To determine if these differences represent a real operator bias effect, or if they might merely be due to chance. I mean, the one operator is always going to have a bigger average than the other 2. One operator is always going to have a smaller average than the other 2. That's just the way it is. Are these differences real? Or are they just the luck of the draw? To figure this out, we need to construct a main effect chart. The main effect chart essentially reorganizes these 30 data from 15 subgroups of size 2 into 3 subgroups of size 10. The analysis of main effect scaling factors, ANOME 0.05, listed in table A19 in the back of the EMP book, allow the construction of limits for the main effect chart based on the original grand average of 175.8 and the original average range of 4.267. We don't need to do additional calculations. We just use the calculations we've already done and go from there. From table A19, page 278, with original subgroup size 2, an original number of subgroups 15, and for comparing 3 operator averages, we find an ANOME 5% scaling factor of 0.589. So the main effect chart limits are grand average plus or minus ANOME scaling factor times the average range. That's 175.8 plus or minus 0.589 times 4.267. You know, 173.28 to 178.32. And operator A is above the upper one, B is below the lower, and C is right on the lower. Operator A is detectably different from B and C. We have a detectable operator bias. Operator A averages 7.8 mils higher than the average for operators B and C. This is 3 times the size of the probable error and 8 times the measurement increment. We need to find out what is causing this bias and take steps to eliminate it. If we do not eliminate this nuisance operator bias, it will continue to degrade the quality of the measurements, and measurement error will consist of two parts: pure error plus operator bias. To estimate the operator component of measurement error, we begin with the range of the operator averages. So the range of the three operator averages is 8.5. Using Formula 10 on page 76, one estimate of variance for operators is found by dividing by D2 star from page 259 and squaring the result. So that's 8.5 divided by 1.906 and the whole thing squared, 19.888. Now, in the textbook, I use a slightly different, more complex formula, but there's so few degrees of freedom here, it really doesn't matter. Earlier, we found sigma PE was 3.8 mils. So sigma PE hat squared is 14.3. So sigma E hat squared, sigma PE hat squared plus sigma O hat squared. So that's 14.31 plus 19.89, 34.2. And this nuisance operator bias component more than doubles the size of measurement error. To characterize the relative utility of the measurement system for this product, we use the interclass correlation, and this requires an estimate of variance of P. As before, we estimate the variance of P by using the part averages. An average for each part. The range for those five averages is 58.167. So sigma P hat squared would be the range, 58.167 squared, over D2 star squared. D2 star for one group of size 5 is 2.477. And we'll square it. The result is 551. Now, with the operator nuisance component present, the interclass correlation is estimated to be sigma P hat squared divided by sigma P hat squared plus sigma O hat squared plus sigma PE hat squared, 94%. Without the operator nuisance component present, the interclass correlation would be estimated as sigma P squared plus sigma P squared plus sigma PE hat squared, 97.5%. So while the measurement system contributes 2.5% of the variation, the operator bias degrades the measurements by another 3.3%. So what do we see? Right off there on the graph, we can see reasonable parallelism, similar test-retest error, a potential operator bias, which we found is real. We estimate the probable error is 2.5 mils. We have an interclass correlation of 0.942 and 0.975 is possible. A flowchart for this type of EMP study is found on page 77 in EMP3. Gauge 130. Harry got Bill and John to join him in evaluating gauge 130. This is a brand new gauge that measured in microns. They grabbed 5 parts out of a basket, labeled them, and each operator measured each part twice. Now, I should tell you that Bill is the engineer that built Gauge 130. John is the operator that uses Gauge 130 every day. And Terry is the engineer who's doing the EMP study. And we look at the graph and we have poor parallelism. And Terry has a big range, the similar test-retest error. Well, to see if there is a detectable difference in test-retest error, we start with a mean range chart. So the mean range chart computes an average range for each operator. Bill 6.2, John 2.8, Terry 14.2. The analysis of mean range scaling factors, ANOM-R 0.05, allow the construction of limits for the mean range chart based on an original average range of 7.733. So we plot the three average ranges, and from page 280, for the original study with subgroup size of 2 and 15 subgroups, and to compare three average ranges, m equal to 3, with alpha of 0.05, the upper mean range limit, 1.699 times the average range, 13.13. Lower mean range limit, 0.38394 times the average range, 3.03. And John is detectably below, Terry is detectably above. Bill and John are operating this thing much more consistently than Terry. And Terry knows it. With different levels of test-retest error, we break the basic EMP study up into three short EMP studies to analyze each operator separately. So Bill is producing measurements that are good to within 4 microns. John is producing measurements that are good to within plus or minus 2 microns. And Terry is producing measurements that are good to plus or minus 8 microns. Since Terry knew he had a problem, he took part 5 back down to the gauge to measure it again. John saw Terry and asked what he was doing. Terry said he was trying to get a good value for part 5. John said if that was the case, Terry was holding the part wrong. Hold it that way and you'll get it crooked in the jig. Terry didn't know the trick. So Terry suggested to Bill that the load spring was too stiff. Bill agreed to change the load spring. 2 days later, they repeated the EMP study with another grab sample of 5 parts. Much better parallelism, similar test-retest error, similar operator averages. We compute the probable error here as 2.3 microns. Now they're all doing as well as John did before. Interclass correlation is 0.98. And the flowchart for this EMP study is found on page 83. And in general, a basic EMP worksheet kind of takes you through the steps one at a time, may be found on pages 305 to 312.
We now turn to Chapter 7 of Evaluating the Measurement Process to consider some case histories of EMP studies.
Well, let's look at a few case histories. 4 operators measured each of 5 parts twice. Who do you like? And why do you like them? Over the 3 questions, we want to look for parallelism. We want to look for similar test-retest error. We want to look at the operator averages. And when you do that, A and C have good parallelism, small test-retest error, and similar averages. Whereas B and D have poorer parallelism, bigger ranges, and possibly different averages, certainly different from A and C. Now you ask them how things are going, they're going to tell you everything's fine. The first step in getting operators to use the measurement system alike is to convince them they're using the measurement system differently. And the main effect chart will help you do that. Here's the main effect chart for truck smoke dimension number 2, A and C, high, and D is low on the analysis of main effects. The mean range chart doesn't show a detectable difference in test-retest error at the 5% level. But the first chart or this main effect chart are key to get them their attention that something's going on. Now you can watch them do this test and not see it. But when you know there's a difference, you catch on. The jig was designed for you to seat the part by pushing on it. B and D, with a flick of the wrist, are pulling on it. And pull versus push is the difference here. When they pull on it hard enough, they unseat the part, gives them a big range and a funny average. Page 98, the compression test, measures the pounds of pressure required to squeeze a foam pad a specified amount. The 5 parts used in this study were selected on 5 different days. We do not expect strong parallelism when the points are all inside the limits, or almost all inside the limits. We expect strong parallelism when the points are going outside the limits, not with them falling inside. There may be an operator effect on both the average chart and the range chart. So let's go to our follow-up studies. The mean range chart shows no differences in test-retest error. The main effect chart shows possible operator bias. But these parts had to relax after each test. So they let them relax 24 hours between test, retest. And they alternated operators. So it was A, then B, then A, then B. So operator B always had days 2 and 4, while operator A had days 1 and 3. And if we look at the values for each part, on parts 2 and 3 and 4 and 5, we see that eventually these parts take a compression set and they no longer fully relax. In other words, they get worn out when they get squeezed enough. And you see that happening with 2, 3, 4, and 5 on day 4. So in this case, we interpreted this apparent operator bias as a fatigue effect on the parts over time. Now, the probable error here, 0.4 pounds. The measurement increment, 0.2 pounds. Basically, these numbers are good to within a half pound. Good to within a half pound is more than enough to tell the difference between 20-pound foam and 30-pound foam. But in this case, when you're trying to make a whole lot of product that's got 28-pound foam in it, you don't have enough discrimination in your measurement system to detect the differences in the product. So here, the interclass correlation is 23%. 23% of the variation in the measurements comes from the production process. while 77% comes from the measurement system. Got a $50,000 test device here, and you're using it to generate random numbers. Then you're using the random numbers to decide how to adjust the process, which shipments to accept and reject, and who gets the meetings this week. You do a study like this, I almost guarantee you'll get to do it over again. Signals from the production process are highly attenuated here, over 52%, before they show up in the measurements. The probability of detecting a 3 standard error shift using all 4 detection rules is still about 94%. So while we can use these measurements to detect large process changes, we really cannot detect any process improvements with these measurements. You can keep a lid on the process with this kind of measure, but you really can't track improvement. Rich evaluated the nanometric gauge used to measure oxide thickness on silicon wafers by having 4 operators measure each of 4 wafers 3 times each. Now, Rich picked wafers that had considerably different thicknesses of oxide. So this is not one product, but it's 4 different products, creating a large range of product variation and squeezing the limits down really tight. Good parallelism, evidence of dissimilar ranges, and possible operator bias. Let's check these out. The mean range chart for the nanometric gauge shows George to have a detectably greater amount of test-retest error. Using the data for Pat, Puneet, and Jamie, we estimate that this gauge has a probable error of 1 angstrom. George, on the other hand, produces measurements that are only good to the nearest 2.5 angstroms. So Rich needs to find out what George is doing differently. He's not getting everything this system can deliver. The main effect chart shows that Pat and George are biased relative to Puneet and Jamie. It's hard to see on the average chart because there's so much product variation, but it's there. Combining the results from both charts, it appears Puneet and Jamie are operating the nanometric gauge up to its full potential. Pat has a systematic bias, but good consistency. And George is operating the gauge in an inconsistent manner that affects both precision and bias. Information you need. Problems that need to be fixed. The manual test stand evaluates an electromagnetic property. Greg used 6 operators and 4 parts to assess how well the manual test stand worked with product T148. You can start just anywhere you like on this one. Everything is going on. Tom and Dan show operator bias. Allison and Dan show increased test-retest error. Dan shows poor parallelism with the others. And what about Jim? Jim's perfect. If you look carefully, The upper range limit is 3.5. You're right on the edge of chunky data here. Chunky data is not a problem for an EMP study, the way it is a problem for a process behavior chart. With an EMP study, chunky data means your estimate of sigma E is getting obscured by the round off. It's not the same as your sigma X being obscured by the round off. If you'll notice, Allison, Tom, Vong, and Acius all have 0 ranges as well. It's the round off that's giving Jim his 0 ranges. So I don't think there's anything unusual about Jim. Main effect chart for manual test stand shows operator bias for Tom and Dan. Mean range chart for manual test stand shows Allison and Dan have excessive test-retest error. So Ashish, Vaughn, and Jim are operating this test stand in a similar and consistent manner. Tom is consistently operating with the manual test stand with a 3-unit bias relative to Ashish, Vaughn, and Jim. Allison had an inconsistent reading for part 1. The reason for this bad reading needs to be discovered. And Dan simply does not know how to operate the test stand. He needs to be taken offline, retrained, and demonstrate his proficiency before you let him produce any measurements in production. In Chapter 8 of EMP3, examples are given on how to do EMP studies which involve 2 potential nuisance components, such as operators and instruments. Examples are given for both crossed and nested nuisance components. Nested nuisance components occur, as in the example here, where you might have 3 plants and each plant has its measuring device, and you have operators inside each plant that use the device in that plant. So operators are nested in plant. And we can compare operators within each plant, and we compare the instruments by comparing the plants. So how to carry out this kind of analysis is illustrated in Chapter 8. The purpose of analysis is insight. And the simple graphic technique known as an EMP study will minimize both the time and the effort between collecting the data and obtaining the insight. Furthermore, the EMP graphs will help you to communicate those insights to others before you lose their attention or get bogged down in explanations of the analysis. Nothing else even comes close.
Now we turn to Chapter 16 of Evaluating the Measurement Process. The automotive industry promotes a measurement system study that is fatally flawed. The following material describes these flaws and provides honest alternatives.
Many ideas develop coherently from a single seminal concept. Other ideas develop incoherently from diverse origins, with little cross-fertilization between the streams. Measurement system analysis belongs to this category, with solutions ranging from naive to overly theoretical, from simple to complex, and from right to wrong. Today we're going to look at the AIAG gauge R&R study. Typically, a gauge R&R study will have 2 or more operators, 1 gauge, and 3 to 10 parts or batches. Each operator will measure each part or batch 2 or 3 times each. Here, the gasket thickness study used 3 operators, 5 parts, and 2 measurements. So the AIAG gauge R&R study starts off exactly like an EMP study. In fact, this is an EMP study we saw back in chapter 6. But instead of creating the average and range chart so that we can see what's happening with our data, the AIAG study gets lost in computations. Here we immediately see we have reasonable parallelism between the operators. There's a possible operator bias for operator A, and the 3 operators have the same test-retest error. Now, some of the computations in the AIAG gauge R&R study are the same as those used in the EMP study. The average range stays the same. The operator averages are the same. The part averages are the same. But the AIAG gauge R&R study proceeds to combine these values in ways that violate established mathematical principles. So we're going to go through this step by step. Step 1, check that all the range values are below the upper range limit. Well, the upper range limit here is 13.9, and all of the ranges are single digits. So yeah, we're clear on step 1. Step 2, divide the average range by the appropriate bias correction factor to obtain an estimate of the repeatability or equipment variation. So EV here is 3.783 mils, which is what we found with our EMP study as well. Next, the range of the operator averages is used to compute an estimate of the reproducibility or appraiser variation. Now, the operator averages have a range of 8.5 mils, and D2 star for one group of size 3 is 1.906. I think these D2 star values were found in the Green Book on page 258. So we take the range of the operator averages, divide by 1.906. Here we square it, subtract off a little adjustment term, and then take the square root, and we get a 4.3. Next, they combine the repeatability and with the reproducibility, and by squaring the repeatability, adding the square of the reproducibility, and finding the square root, 5.7 mils. Step 5, the product variation is estimated using the range of part averages. The part averages have a range of 58.167 mils, and D2 star for one group of size 5 is 2.477, and the ratio gives us 23.5 mils for the product variation. Finally, step 6, the total variation is estimated by combining the square of the equipment variation, the square of the appraiser variation, and the square of the product variation, and then taking the square root. So our total variation, 24.2 mils. Up to this point, everything is okay. While these estimates are not the only estimates we could have found, and while they may not be the best estimates possible, they are all reasonable estimates of these various quantities. The formulas used here you may find back on page 76 as some of the alternate formulas that could be used. The train wreck begins with step 7, when the gauge R&R study tries to use these estimates to characterize relative utility. In the current version of the gauge R&R study, the first 4 quantities in the list above are expressed as a percentage of the last value. So, step 7, the repeatability is divided by the total variation, 3.78 over 24.2, and this number is interpreted to mean that repeatability consumes about 16% of the total variation. Step 8, the reproducibility is divided by the total variation, 4.3 over 24.2. And this number is interpreted to mean that the reproducibility consumes about 18% of the total variation. Step 9, the combined R&R is divided by the total variation, 5.7 over 24.2. And this number is interpreted to mean the combined R&R consumes about 24% of the total variation. And step 10, the product variation is divided by the total variation, 23.5 over 24.2. And this number is interpreted to mean that the product variation consumes about 97% of the total variation. But since when does 16% plus 18% equal 24%? Likewise, when does 24% plus 97% equal 100%? Realizing they had a problem and not knowing what else to do about it, the authors of the gauge R&R study decided to insert a statement at this point. The sum of the percent consumed by each factor will not equal 100%. No explanation is given for this statement. No guide is offered on how to proceed now that common sense and every rule in arithmetic have been violated. Just the simple statement that these numbers do not mean what they were just interpreted to mean, and the users are left to their own devices when it comes to making sense out of this nonsense. Well, why don't the percentages add up? Obviously, the ratios computed in steps 7, 8, 9, and 10 are not percentages. So what are they? Considering how the basic quantities were computed in steps 2 through 6, we can show the relationships between these basic quantities using a couple of right triangles. So the equipment variation of 0.1565 with a little bit of manipulation can be expressed as the sine of angle A times the cosine of angle B. The appraiser variation of 0.1777 with a little adjustments can be expressed as the sine of angle A times the sine of angle B. Combined R and R of 0.2368 is simply the sine of angle A. And the product variation of 0.9715 is the cosine of angle A. These ratios were dressed up as and interpreted as proportions. They are and always have been nothing more than trigonometric functions. And that is why the ratios do not add up. Multiplying by 100 does not make a trigonometric function into a proportion. Trigonometric functions do not satisfy the conditions needed for a set of ratios to be interpreted as proportions. A set of ratios will be proportions if and only if the common denominator is the sum of the numerators. It is the additivity of the numerators that is the essence of proportions. And in an R&R study, it is not the standard deviations, but the variances that are additive. That's the law. By ignoring the requirement of additive numerators when computing proportions, the AIAG gauge R&R study acts as if the Pythagorean theorem does not exist. As a result, it grossly overstates the effect of measurement error. We will consider how to correct steps 7, 8, 9, and 10 shortly. But first, we need to look at some additional nonsense that is part of the AIAG gauge R&R study. Steps 11, 12, and 13. Undeterred by percentages that do not add up, the AIAG gauge R&R study continues by comparing equipment variation, appraiser variation, and combined R&R with the specified tolerance. Prior to 1984, these values were multiplied by 5.15, divided by the specified tolerance, upper spec limit minus lower spec limit, and then expressed as a percentage. Today, to inflate the implied damage, each of these values is multiplied by 6, divided by the specified tolerance and expressed as a percentage. So, for our example, the specified tolerance is 80 units. So in step 11, the repeatability is said to consume about 28% of the specified tolerance. While in step 13, the combined R&R is said to consume 43% of the specified tolerance. As before, these ratios ignore the geometry of the vectors involved, and so end up overstating the damage due to measurement error. The product variation axis is going to lie along one side of a right triangle. The measurement error axis is going to lie along the other side of a right triangle. And the product measurement axis is going to lie along the hypotenuse of that right triangle. And it is the product measurements that have to be compared with a specified tolerance. So for step 13, for example, the correct value for the combined R&R is sine of angle 14 times 0.429, or 10%, rather than the AIAG value of 43%. For step 11, the correct value is 4% rather than the 28% found. And finally, step 14. The AIAG study concludes its computation of spurious values by computing the number of distinct categories, or NDC. We take the square root of 2 times the product variation divided by the combined R&R, 5.8. NDC values greater than 5 are considered to be good. However, this value does not actually define the number of categories for the measurements that fall within the natural process limits. While NDC is related to the interclass correlation plot, it has no simple or useful interpretation in practice. I know I spent years trying to figure out how to explain what this ratio meant, and this bottom line is my conclusion. Well, that brings us then to the guidelines. Now that we've computed all these spurious ratios, how do we interpret them? Since 1962, the AIAG gauge R&R study has been revised 5 times. The formulas have changed, and the funny ratios that are not proportions, even though they are interpreted as proportions, have been defined with various numerators and denominators. The numbers mean just what I say they mean. So even though the Red Queen has revised the formulas in the past, and may continue to revise the formulas in the future, the guidelines for interpreting these funny numbers have always been ratios less than 10% are said to be good. Ratios between 10 and 30% are marginal. Ratios exceeding 30% are unacceptable. Applying these guidelines to our example, we find that this measurement system is simultaneously good, marginal, and unacceptable. Any questions? In spite of the differences between the two columns, the same guidelines are used for interpreting both. This is presumably one of the benefits of using guidelines that have no contact with reality. Since no justifications for these guidelines exist, they can be adapted to fit any set of ratios that might be computed. After all, when attempting to interpret patent nonsense, it's always best to use arbitrary guidelines. Well, how do these guidelines match up with the 4 classes of monitors? Well, the relationship between the gauge R&R ratio and the interclass correlation coefficient, the combined R&R is the square root of 1 minus the ICC. Using this correspondence, we can set up 2 scales. On one scale, we will plot the values of the percent combined R&R ratio in this ascending order, along with their interpretation from the guidelines. So you've got good and marginal and unacceptable according to the combined R&R ratio. On the other scale, we plot the values of the interclass correlation in descending order, along with the 4 classes of process monitors, first, second, third, and 4th class monitors. So that for each scale, desirable values are on the left, while undesirable values are on the right. And then we can use the lines to connect the corresponding values on the 2 scales. So, according to the AIAG guidelines, a good measurement system is one with an interclass correlation in excess of 99%. Well, I'm sure everyone would agree with that statement. A marginal measurement system is one with an interclass correlation between 99% and 91%. And here we begin to see how conservative the gauge R&R ratio and guidelines are. And measurement systems with an interclass correlation less than 91% are rated unacceptable by the AIAG. On the other hand, first-class monitors will have a combined R&R ratio below 45%, 0 to 45%, first-class monitor. Combine R&R between 45 and 71%, you've got a second-class monitor. Combined R&R ratio between 71 and 89%, you've got a third-class monitor. So the choice is clear. Do you want to condemn your measurement processes? Or would you prefer to use your less than perfect data to operate and improve your processes? Well, how do we do an honest gauge R&R study? Using the relationship between the variances seen in step 6, the variances are additive, we discover the true proportions inherent in this problem when we divide both sides above by the square of the total variation. So, honest step 7. Repeatability is found to actually consume 2.4% of the total variation, rather than the 16% erroneously found earlier. An honest version of step 8, reproducibility would be found to actually consume 3.2% of the total variation, rather than the 18% erroneously found earlier. In an honest version of step 9, the combined R&R would be found to actually consume 5.6% of the total variation, rather than the 24% erroneously found earlier. And if we note the repeatability 2.4% plus the reproducibility 3.2% adds up to the combined R&R of 5.6%. Duh. And in an honest version of step 10, the product variation would be found to actually consist of 94% of the total variation, rather than the 97% erroneously found earlier. And now we have properly accounted for the components of the total variation. So when you use the AIAG gauge R&R study, what can we learn from the AIAG gauge R&R study? By ignoring the Pythagorean theorem, the gauge R&R study converts good data into values that are hopelessly flawed, resulting in an analysis where virtually nothing is true, correct, or useful. Once you ignore the Pythagorean theorem, mere guidelines are not going to remedy the situation. After step 6, every aspect of the AIAG gauge R&R study is erroneous, fallacious, naive, incorrect, and to put it quite simply, wrong. So if you want to obfuscate and confuse the issues, if you want to needlessly condemn measurement systems, and if you want to continue to beat the vendor over the head, then by all means continue to use the AIAG gauge R&R study. The more you use an AIAG gauge R&R study, the less you will know. But there is an alternative. However, if you want to learn how to use imperfect data to make better products, if you want to get the most out of your imperfect measurement systems, if you want clear answers to straightforward questions, then you need to learn how to use a full-fledged EMP study, or at the minimum, an honest gauge R&R study. Well, you know more than you think you know. I have tried to raise your awareness regarding a different approach to making sense of your data. But superstitious learning is how we know what isn't so. And you are going to run into a wall of resistance made up of superstitious learning, both on a personal and a corporate level. The only way over this wall is to take a leap of faith. This happens when you trust the chart to tell you when to take action and when to avoid taking action. As you use the charts, you will begin to explain process behavior, which will reinforce the understanding, which will reinforce the use. You see, SBC is a way of thinking with some tools attached. Learn the tools, and you don't have much. Practice the way of thinking, and the tools come to life. Now, as you practice, you will have questions. When this happens, drop me a line, and I will see if I can help. Thank you for spending the time to go get through this class. Now, go use what you have learned.